Good morning, everybody. Good afternoon. I just woke up. At least you are awake. I've decided that we do the presentations over 3 hours. So we start on Thursday afternoon, 3 o'clock, with presentations, and then for another 2 hours on Friday. And so that leaves us 15 minutes per group. And it will be absolutely strict. After 15 minutes, you go. Okay? So you can't go into the time of someone else. You must stick to the 15 minutes. Okay? Furthermore, I want everybody to speak. At least 1 minute. At least. But the way you divide it in your group, don't want any rules specific that you have to divide it equally or something like that. You can divide it, have a main speaker and some people who then cover specific aspects, or you can divide it up so that you have equal times. That's up to you. But everybody must speak. Okay? And the other thing is, we would like to have you submit a written document. And again there, I want proof that everybody has contributed. And one way of doing that is let everybody write a paragraph with his or her name on it. So so everybody must be part of the process. You can then decide who writes what and how you put it together, but we want to be sure that everybody has contributed to the written document. Yeah, that's all. Any questions on that? Yes?
Like the format for the written report.
The format?
Yes.
I would think it should be at least two pages per group, but it can be considerably more if you want to. I think some of you are doing graphs and collecting things and so on. You can put that there. So I don't think, Emma, what do you think? Not an upper limit, really. Huh? Well, there would be too much in any case. But I think it should be at least 2 pages per group. And I think you find it difficult you just have 5 paragraphs. That is 2 pages normally. But
I was looking at the format itself.
the format.
Yeah, introduction, things like that. I don't know how when
Emma wanted to have a discussion with you on. Emma, there's a question now about the format. On the presentation itself. But on the document, I think it would be good to have an introduction and then to have several points which you discuss in the introduction, how they link together, and then you just have several sections in which the different points are described. I think when you do your essay at the end of the year, there will be a strict rule how you do this. I don't think we want it too much that way now. We want to leave you some room for your creativity to do it the way you wish to do it. Okay. Now, last time I made a mistake at the place where we derived the black body radiation, and it is at this point where epsilon I no, the Ni, the average value of Ni must be 1 over beta I don't think I had this 1 over beta there, and so if you have notes and you can't figure out how they work, if you put that in, then you will see that everything works out. And in the differentiation of this one, which was I left out a step. It was sort of a very quick towards the end of the lecture, and Andre actually pointed out that I left out that step, so I don't know whether you caught on to that. This log z was, so it's and so if you differentiate that, then you would have to do it in 2 steps that you get. So if I differentiate that, then I get, this comes under the line, but then I have to differentiate that again, and that comes on top of the line. And then these things go away, and then dividing through this gave them the end result, which was then 1 over exponential beta epsilon r minus 1. So the result which I wrote down was correct, but I left out this step, and so it wasn't so clear what I was doing. So that's just a small correction. So we have a formula for the black body radiation, and I'll just show this like this. This is a picture of the black body radiation. As you can see in, if you Google it, from the sun, the radiation from the sun looks like this. And what you see is that the radiation which we get on the surface of the Earth is not exactly the black body radiation. There are all sorts of chunks in here cut out and so on. You can Google this, just radiation. And these are due to absorption, because the radiation comes from the sun and then it goes through the air, and the air absorbs the atmosphere absorbs part of the sunshine, and that is not even, it is in certain chunks, at certain areas. And now, so I want to just say a little bit about these different ways of absorption. So if we look at the air, what is it that we have in the air? We have molecules, and the molecules are built of atoms. And what can molecules do when they get excited? They can, if light comes here and it hits the molecule, this molecule can rotate. So we have a rotational spectrum of the molecules. And that rotational spectrum is the lowest energy. And that energy is given basically by, and I'll write down the formula without deriving it. So what we have is we have similar formulas, the mass times the radius, the size of the, and that gives the moment, the inertia of the rotation of the molecule, and then this is basically L squared, the value of L squared, which in quantum mechanics, and we will come to that. A quantity like L squared goes into L times L plus 1 times h bar squared. So that is the angular momentum squared divided by the moment of inertia. And this value, you can put these in. And for a molecule, the molecule is the mass of the molecule, say oxygen and so on. And so you have these things rotating, and you can calculate that. And that happens to be I'm now drawing here the black body radiation. That happens to have a very long wavelength, the rotation part. So it's up here. So where there's actually very little of the light coming in. So the rotational spectrum has a very high energy, and you can actually calculate it by just putting in the value of M and R for a typical molecule. And these L values can run from 1 to and so on. So you get these different L values, and you know what H bar is, and you can calculate the spectrum of the rotations, which is right up here. And then you also have the possibility of the atom itself being excited. There's an atom here and there's an atom there, and they can be excited. So what is an excitation of an atom? Is the light comes in and it hits out an electron or pushes it up to another level, and then it drops back, and that energy absorbs then of that light. So that is the atomic absorption, and that lies right here on this side of the sun's spectrum, and we will calculate that, but not today, but tomorrow. We will calculate this absorption of the light on atoms, but in between these two there is a part which is extremely important for us, and that is the molecule can vibrate. So this molecule can go out and in and out and in like this, and that spectrum lies in between here. And so this actually makes these holes in this spectrum. I mean, I'm now talking order of magnitude. It is actually interesting that many of the molecules do not, even though I said that's what they do, they don't do that. But the reason for that is something else, which I will explain. So I would like to discuss the case of a simple molecule, the simplest we can think of, and that is a diatomic molecule. Two atoms, and they are connected. And then this thing can rotate. Now there is something. These molecules have, these atoms have almost equal mass, and so there's one thing we have to do differently from what we did with the sun and the earth and so on, is we will have to go and introduce what we call a reduced mass. We actually need to do that for the sun and the earth as well, but it doesn't really matter, because the earth is the sun is so heavy relative to the earth that we can neglect that. Now the reduced mass just means that we have this value R1 here, and this is the coordinate R2, referring to atom 1 and atom 2, and so these two atoms, they can move together with the center of mass, and the center of mass is given by m is this R is equal to m1 R1 plus m2 R2. So this defines a new coordinate R, which is the coordinate of the center of mass. And if we look at the kinetic energy of the molecule, then it's this coordinate, which we need. It's the center of mass that moves kinetically. But and then we also introduce a vector R, which is the difference between R1 and R2. And so this is how far they are apart. This is the this distance, and if one goes through this, you see what you have to do is you have to associate with the movement of the vector r, you have to associate a mass mu, which is given by 1 over m1 plus 1 over m2. So if you calculate this mass, that we call an effective mass for this. And then this is again a one-body problem. So here we have a two-body problem. We've divided it into two one-body problems. One where the center of mass moves, and the other where the things move relative to them. Okay, so that's just an attempt to keep honest here, that we write these things in. As I said, in the case of the sun, the earth and the sun, we should also have done this, but one of them is so much larger than the other, so that we don't really need to worry about that. Now, how does this the potential look for this movement, this motion, which I'm worried about here? The potential looks like this: that these two atoms cannot come too closely together, because then the electrons which go around each of them, they get in each other's way. They don't like to be so close together, and so they will have a force which shifts them apart. And so the potential will look like this. They can't be too close together, but they share the outer electrons. They share, and this is the way molecules are being built, that the outer electrons decide to go around. They want more space, and so they regard it better to go around both of these nuclei, and by that they draw them together, and so that gives an attractive part here, and so the potential looks something like this. So the outer electrons are being shared by these two atoms. They go around both of them, and by that they can reduce the energy. They have more space in which they can reduce the energy, but they can't. But the inner electrons, or in the case of hydrogen, where you don't have inner electrons, it's just the two protons, the two nuclei just push each other apart. And so this is a typical potential, a molecular potential between two molecules. It would typically look like this. And so what we now do is what we did before, we approximate this for the lower part here by an harmonic oscillator. So then the harmonic oscillator looks like this: p squared over 2 mu this is the classical form. But we need to do this in quantum mechanics, because the distances are short, and we are of the order of h bar omega. So how would you do this now? How do we solve this problem? We want the motion of these two, the vibrational motion, and this is what this is called, the vibrational state. It vibrates. So we want to find the energies at which it vibrates. We have a potential and we have a momentum. So how do we solve a quantum mechanical problem? Schrödinger equation. Okay, so let's do that. So what do I do? I write this as a operator. So convert it to an operator. So what I do is I write it as because P is okay, and then I write here x stays x, and I multiply this with psi x, and that gives me e psi x. And so this is a differential equation. Psi x, what conditions do I have on psi x? Far away it should be 0, yeah, that's right. So psi x should be 0 here and psi x should be 0 there. Huh? Far away, huh? Should go to 0. And so I need solutions of this differential equation, and which I can find for different values of E. What do we call this equation? What is it? It has a name. Yeah, it's an eigenvalue problem. So this thing will have different values of E for which this equation will be satisfied. And it is like the problem we did in the box. There we just said the potential was 0 everywhere, and then it was infinite and infinite. And now we say no, the potential runs like this. And so I will solve this equation by drawing I'll show you the way the solutions look. I won't solve it this way. I will then later go over to another method where we don't go to the Schrödinger representation and show you then how we can solve that. But if we are the standard quantum mechanics textbook, we'll do this in the Schrödinger form, and it will say you have to solve this equation. And the way you typically do that is you write a polynomial expansion for psi, and you compare terms on both sides, and then you fix things, and then you have, in this way, you create solutions. And this one is a standard form, which is done in that way, and in other ways. There has been studied in many, many cases. And so what you find here is that you get a solution. Maybe I need still another color. You get a solution at this energy. And then you get another solution at that energy. And then you get another solution at that energy. And so on. And it looks like that. And the values of E, and I'm telling you this now, and I'm going to show it to you in another way, that this is correct. The values of E are n plus a half times h bar omega, where omega is the square root of k over this mu. I've already made it an m again. Let's make it a mu. Where's that? So this is the frequency of the harmonic oscillator, the classical harmonic oscillator, and these are the energies. They are discrete. They are only specific values of the energy for which you will have a solution which will go to zero for both sides. If you choose another value of energy and you try to solve this, then the solutions will blow up. It will not be, and you will not be able to normalize it. So it's only for these values that the solution will not blow up, and it will look like this. So we take this here, and I draw a graph here, and so the first solution, this lowest one, will look like this. And the second solution which I'll draw here will look like this. And the third solution will make, so we say this has one node, which we know already from the square box that we had solutions with one node, with no node, and with one node, and with two nodes, and so on. So it will be the same here, and this will look like this, with two nodes, and so on. And so the general solution are specifically well-defined polynomials, which are called the Hermite polynomials. They look like this, and the mathematical expression so in general, psi is given by the so-called Hermite polynomial as a function of whereby H1 of this thing, which I will just call psi, is equal to 1. H2 of that is equal to 2 psi. So that goes through once through 0. And oh, sorry, that's no, this is H0 and H1. And H2 of it is minus 2 plus 4 psi squared. So that's a parabole. It has it goes through 2 zeros. And so you can look them up. They are in books, and you can look in any quantum mechanics book. They will show you the whole list of Hermite polynomials. And so you have explicitly the solution of this harmonic oscillator potential in quantum mechanics. And it plays a central role. It's something which is good if you know it, because it is being used very often. I want to show you something else. To solve that problem, I want to do it in a different way. I don't want to go to the Schrödinger equation. I just want to work with the operators themselves. And the reason why I do this is, well, first of all, it's much nicer. It's not as messy as writing down polynomials and so on. But secondly, it's a method which is widely used in physics, in quantum physics, that one works with the operators themselves and not within their specific representation. So in order to do that, I remind you that the equation we want to solve is this one. And just allow me to change mu back to m, because otherwise I get confused. And then where m is, you can always put mu, or you can put it that way as well. And so what we will now do what did we say was quantum mechanics? We said quantum mechanics was the necessity to put in a commutator, that the commutator of the position and the momentum is not zero, and so and that this is I h bar. I wrote it this way. And in future, when I write it this way, that it's this what I mean. I just showed it a little different for you, so that you do not get confused too quickly. But so normally we do not show the operator directly. We say that's an operator, and so let me just write it this way: xp. These are now all. This will be operators. And these operators will have a property which we call Hermitian. They are Hermitian, which means that their eigenvalues will be real. So they'll have real eigenvalues. And anything that I measure, anything that is physical, must be Hermitian and have a real eigenvalue, because my measurement is something real. And so I will now just use this, nothing else, to solve the equation for the harmonic oscillator. And in order to do that, I construct two new operators. So this is actually just a question of giving them weighing the x plus ip with different weights. These are just numbers. And I introduce a conjugate operator where I make this minus ip. The rest is the same. X. Okay. Now we can we construct a quantity. This is now not a Hermitian operator. If I take the this is the Hermitian conjugate of that one. So they are not equal. These are not Hermitian operators. So if I take the Hermitian conjugate of that one, I get this one. And now I want to write down A dagger A. And so that's easy. I take this one with that one. That gives me m omega over 2h bar x squared plus, okay, p squared, and this gives me okay. Am I finished? Yes. And p squared, but it means p times p. And x squared means x times x. What about? No, I'm not going to the Schrödinger picture. These are just operators. Okay? But you have something which is worrying you, and it's good that it's worrying you. Who else is worried? You're also worried.
Yeah, we showed that E and X don't commute.
Yes. Yes. So if we now multiply this with that, well, let's do that. So we get I, this I, and then this with that gives me xp, and there's a term here, square root of m omega over 2h bar, and then it's 1 over 2 omega h bar omega, and then it is times xp, and then I also have to multiply this way, and it gives me minus xp, minus px. And so that is the commutator. Okay, now we can simplify this a little bit. We can throw this guy out, and we can throw that guy out, and this will become 1 over 2h bar. And there's an I here and an I there, so that's minus. And then it's multiplied by h bar. So that goes out with that, so that's just a half, that thing there. And these things I don't really want to simplify now, but I see if I multiply this by h bar omega, then I in fact get here p squared over 2m. Okay, so I'm going to multiply this by h bar omega, and then I get the h bar goes out, m omega squared over 2 x squared. That's right. Yeah, and that is this plus p squared over 2m. And this one is minus a half h bar omega.
The square of 1 equal to you're supposed to give plus or minus 1 equal or plus or minus half.
Yeah, you're right. I choose the plus. Let me think about it. Maybe I'll answer you tomorrow. Huh? What would happen if I use the minus here? It will give a minus there, but that would worry me actually at the moment. So what I have here, oh yeah, and here's this. Sorry, there's a dagger A. so this thing is h. So I can write down h is equal to a dagger a plus a half times h bar omega. So, and this thing I can, this is just a Hermitian operator. If I take the Hermitian conjugate of this, I get the same thing. Yeah? So this is an operator that measures something. Okay? And so I will call it n, and then I'll write a half h bar omega. So I have h is equal to n plus a half h bar omega. And I needn't tell you this now, but I did tell you already what was the answer for E. It is this. So if n has the value, big N has the value of small n, then this is exactly what I get. But I'm not going to use that as an argument. I'm just showing you we are still on the right track. I'm not going to use that as an argument. So the next thing we want to do is we want to figure out what is this n. And in order to do that, I just want to calculate something else, and that is this commutator. So we have already calculated one part of it. So why don't you calculate that commutator? Just go and calculate it. You know how to do it? Know what that means? So we already have calculated this. So you must just calculate the reverse side. Can you do that? Can you do that? Calculate the commutator. You explain exactly what you do. Huh?
You have already calculated this one, and now consequent. This 10 times this one. And wait, square. This one, this one. And this one, this one. one is equal mine. Mine.
Yes.
P. It's equal to H bar. Because if it is one, this one, this one, this one, and the
You forgot to each bar.
two.
Yeah.
Minus plus I. That's all.
Now you add, subtract.
And I calculate this. I calculate this one. I will get a. In this time, A plus I they get A and A they get have the first the same first term. This one and this one. This one minus this one is equal to 0. And the rest is R minus R.
Okay, very nice. So let me again make this point. This way of working is an efficient way of working with many quantum mechanical problems. And it is easier than to work with solving differential equations all the time. But we haven't really progressed that far. We've just calculated this quantity. Is everybody happy with this? Any questions? Anybody who says, I haven't got a clue what this means? So let's get it sorted out. If you don't have a clue, just say. Do you know what this means? Not? Do you know, have you worked with commutators? Commutating quantities? Or maybe we need to talk. You must come and talk to me about this specific problem. Do you also, you know how it works?
Yes.
You understand it?
Yeah.
You don't understand?
Mathematically, yes, but for physics.
You don't understand the physics. No, we're still far away from the physics. We're just finding a method of doing certain things. Huh? Okay? The math's okay. I'm talking about the steps. Okay. It's break time now, so let's take a quick break. So someone remarked this one is an operator. Yeah, it's an operator. It operates on whatever comes behind it. But we can just handle it like a number also. It will not change. Yeah. The other thing I would just like to say, this we already said that this n is a Hermitian operator. So it will have, I can do, quite abstractly, I can do an eigenvalue problem of it. I can say this operator operates on some state n, and the result of this will be n, that will be the eigenvalue, and I call it also n. I mean, this is the way I handle it abstractly. So this, But I don't claim that n is at this stage that this is that this is an integer. I just write n. We know from this other problem that we're expecting this will be an integer, but we don't know yet. So what we want to do is we want to look at what is the function of this n and this a? I mean, what are they really? A lot of students said to me, the mathematics no problem, but they have problem with the physical interpretation. Well, that's good, because that's what we're now going to concentrate on the physical interpretation. So let's just calculate a few things. For instance, let's calculate the commutator of A and N. And you must trust me that this is not waste of time. So this is the commutator of A of A dagger A. So if I calculate that commutator, it goes like calculating commutators, goes like differentiation. You calculate that commutator, and then you pull this to the front, and then you calculate that commutator. So the first of all, it's this is equal to A commutator. You can write this out too if you want to, that this is in fact the case. Maybe we should even do that. So if you have three commutators, you can just write out. You can say it's the commutator with that, and then you put in two other terms, and well, maybe I can leave it to you. Now, what's this commutator? Okay, and what's this commutator? Okay, so this is just equal to A. This commutator. Okay, and now I want to calculate this commutator. And this gives me a dagger A, and so that again this commutator is 0, and then I put A dagger in front, and I calculate that commutator, and that is speak up. -1, no? So that's minus. Okay, so I have these two commutators. And now I want to look, what does A dagger do if I put it onto N? Rising. Okay, so let's see how it works. So I want to, I construct this thing. This is a state, and I can just put A dagger to it, and then I want to calculate this. And now I know that A dagger N plus minus N A dagger is equal to minus A dagger. So for N A dagger, I can put is equal to A dagger N on N, and then I take this one over to that side, and then plus A dagger N. And this on that is what? That is just N. This is what how we defined N. Huh? And so I get that this is N plus 1 times A dagger on N. Now this is a state, and this is a state, this is a state. So I've been able to construct out of this state a state for which the N value is 1 bigger. Okay? And there's nothing strange about this specific state. I can do this many times. So every time I put in A dagger, so let me do a drawing. I have a state N here somewhere, and I apply A dagger to it, and then I get to the state. I get to that state which has the value N plus 1, which in some way is N plus 1. It has the eigenvalue of N plus 1, of the N plus 1 state. And if I do it again, I go to N plus 2. And so I go up. By just multiplying the state each time with A dagger. So what we call this operator is a raising operator. It raises the excitation. In certain fields of quantum physics, it's also called a creation operator. It creates an excitation, an additional excitation. So it creates something. Okay? And so I can, if I start somewhere, I can go through, I assume we have something like this, but we don't know yet. But I can raise them as I go with this operator. And now I want to see what does the operator A do. If I have N and I put an A in front of it, then it's the same thing. I have to look at this equation, which is AN minus NA is equal to A. So I want to calculate NA. I want to see what is this state like. So NA becomes AN minus A. So that is NA on N minus A on N. And so what this, sorry, I made a mistake here. Other way around. AN. So NA is AN minus A. I bring that over there. And so I get this on that gives N. So I get N minus 1 times AN. And so this operator obviously goes the other way. It takes the N state to the N minus 1 state. because the eigenvalue of n of this state is n minus 1. So that's the n minus 1 state. And if I do it again, then I get to n minus 2 and so on. So I go down. And so we call this operator a lowering operator. It lowers, the one lowers and the other one raises. Or in the other language, we call it a creation operator and an annihilation operator. Or destruction operator. It destroys something, annihilates it. And so I'm almost finished, except that the question is, I still don't really know what n is. And if I keep doing this, I run to minus infinity. But I can't run to minus infinity because with n, because I have an Hamilton operator here, and it must stop somewhere. So there must be a value. There must be a value, say, of n0. If I lower it further, if I try to go further down, then I must get 0. So it must stop me from going further down, which is basically also the way in quantum mechanics, quantum field theory, the way one defines a vacuum. There's something where there is nothing anymore, so you can't destroy it. So if you try, you get 0. And so this thing must be 0. And so I must start from this 0 state, and now I can operate on that with a dagger, and then I get to the state 1. And now I know, because I had to choose 0 here, I know that this value of n, which I get here, is 0 plus 1. So it is it's a integer. So then this state is then 1, and this state is then 2, and this state is then 3. And so I see that the spectrum of H is indeed integer numbers here plus a half times h bar omega. And that's exactly what I had written down here. Without doing these differential equations and worrying about boundary conditions and so on, we were able to do the harmonic oscillator, find the spectrum of the harmonic oscillator. There is a simple way of calculating the Schrödinger representation of this from this very condition, which is also very easy. What I need to do is I need to say, I need to use this result. This result. I need to use this result and then get a simple differential equation for it, because if I write this thing now in the Schrödinger picture, then I know I will get that m omega over 2 h bar x plus I h over I times I d dx of the state which I will call u0 of x, is equal to 0. And so this is a simple differential equation, which if I introduce psi is equal to m omega over h bar x, just to make the equations look simpler, and then I get here psi plus d psi u of psi is equal to 0. And the solution of that equation is, of course, u0 is equal to some constant about e to the psi squared over 2. This satisfies this equation, and so I again get the form which we had initially for u0. So this is then the Schrödinger representation of the problem, but only going into the Schrödinger representation after we finished actually solving the problem. So that is just a way of displaying what the result is, and not a method of solving it. We solved it without going to that. Now I've confused a few more people. Is that okay? And now all the other states. So what I'm claiming is I've derived this equation, this form. Yeah, I've derived it. Huh? Just put this stuff in again, but it's a Gaussian. I derived that form by just using this result that I have to stop my chain somewhere, and just using that as the condition for the zero state, I can then, with a simple differential equation, get the solution of this, and not with a second order differential equation. And if I want to find any of the other states, then the only thing I need to do is to take a dagger and write it in this form. So we will get a minus there, and apply it to this. Because that is the first excited state, is defined by applying a dagger to the ground state. And now I put the a dagger into the Schrödinger representation, and so I get the first excited state, and I get it as a Schrödinger state. And now I can run with this up as much as I want, and we'll get the same results as the Hermite polynomials. I think this has been enough for today. I think there's still some time for questioning. Questions? Just those of you who said they didn't understand the physics. Does it make sense now? Not really. Many applications specifically where there are symmetries. I've used this method, where you work with the operators. For instance, if you have the generators of a group theory, they could be operators. You do group theory, and the generators could be operators, and they have such structures. And you don't need to write everything in differential equations. You can just work with the generators and find the relations between them. And they are also in group theory, they are commutation relations. So what I'm trying to show you in this, and we've done a specific problem for our energy problem, which is how does the vibrational spectrum look? That is what we were addressing. But I've showed you in trying to solve that, I showed you a method which obviously not many of you, some of you have probably seen it before, but it's obvious that many have not. You've not seen. Who's seen this method before? You've seen. Yeah? And you know it. Understand? Yeah. Yeah. Okay. Yeah, question? The emission of this of the state. I've just talked about states. There is something very interesting actually. What if we're worried about carbon dioxide? Huh? Everybody's worried about carbon dioxide. What do you think? How much carbon dioxide is in the air? Now, in the bad times, how much is it? Too much. Okay. How much? I think it's something like 30 parts per million. It is very, very little. Okay. And what is and we all know that the atmosphere is mainly nitrogen and oxygen, and these are molecules of nitrogen and oxygen. And for those who have looked at some of the absorption spectra and so, have you seen that the atmosphere absorbs the sun, the nitrogen and the oxygen in the atmosphere absorb the light? Think they do? I mean, if they did, we would be all sitting in the dark. They would just take out all the... There's so much, I mean, the air is basically O2 and N2. And they are they are diatomic molecules. But they do not cut out the light for us. They let it through. And the reason for that is I'm saying that because you're asking about what's the interaction between the light and the states which we have here. The reason for that is that they have two equal atoms, oxygen and oxygen atom, and that means that there is no polarization. And this is something we have not discussed, but there's no way that the charge of the molecule can be different from the place where the center of mass of the molecule is. And that means that the normal thing, which one formally calls an E1 transition, the main electromagnetic transition of light, does not occur. And that's why the oxygen and nitrogen let the light through. In the area, in this band, which I discussed at first, between the atomic and the rotational part, in this middle band, the light goes through. And now you can ask, well, what happens with carbon dioxide? Well, in fact, carbon dioxide is also a molecule which has an oxygen and an oxygen and a carbon in the middle, and these are doubly bound this way, and that is also a symmetric thing. So when carbon dioxide tries to oscillate, like getting the two oxygens to oscillate around the carbon, there is no way it can be done by the E1 transition, by the absorption. It cannot be done. So carbon dioxide, in terms of this vibration, also does not absorb any light. But what carbon dioxide can do, and we will not treat that, but it can wobble. It can do a motion like this. That these go this way. So it does this. And it's that sort of motion that absorbs light. Because there the charges are not balanced. So you can absorb light in this way. And so carbon dioxide, and that's where the whole business about carbon dioxide comes from. And then there are, maybe I could just say as a last thing, water, H2O. The O sits in the middle, and the H sits for some reason at an angle. The two H's sit at an angle. And this thing can wobble in all sorts of ways, and it can be excited by light, and it in fact is a major absorber of our light. And so that in terms of certain areas, you will see that the amount of light and heat that comes through is very much higher in a area where the humidity is high than it is in an area where the humidity is low. So it's actually much more complicated than we will be able to discuss here, but at least we will get certain ideas of where these different things come from. I think you can start working on your project, and I will go now. Thank you very much.